Hello, Matt here from chemistrystudent.com. In this video, we're going to look at orders of reaction. We're going to talk about what orders of reactions actually are, including 0, first and second order with respect to a particular reagent, and how changing the concentrations of reactants can alter the rate of a reaction in different ways. Before we talk in detail about orders of reaction, it is essential you are comfortable with what we mean by reaction rates. Rates of reactions have been covered in much more detail in a separate video. Check the links in the description below. As a short outline for this one, however, rates of reaction describe how quickly reactions are occurring. They can be measured in terms of the speed at which reactant concentration decreases or the speed at which product concentration increases, given the units moles per decimeter cubed per second. A very quick recap done, let's go. As reactants are needed for a reaction to occur, it makes sense that the rate of a reaction can be affected by the concentrations of reactants present. If the concentration of reactants in a reaction mixture is increased, this usually means the rate of reaction increases. This kind of makes sense. The more reactant particles there are, the faster the reaction can happen. However, sometimes the rate of a reaction doesn't change by the same factor as the concentration of reactants has. For example, doubling the concentration of a reactant may cause a reaction rate to double, as in the reaction happens twice as fast. Or in some cases, it may make the reaction rate quadruple, happen 4 times as fast. Equally, there are some cases where changing the concentration of a reactant doesn't really affect the reaction rate at all. We describe how the rate of a reaction is linked to the concentration of a reactant using orders of reaction. There are 3 orders of reaction that you should know: 0 order, first order, and second order. They are written as a small number as a superscript to the reactant in square brackets. We describe a reaction as being 0, first or second order with respect to a particular reactant. This just means that we are talking about how the concentration of a specific reactant affects the rate of the reaction. This is quite important as many reactions have more than one reactant, and these reactants can each affect the rate differently. This has been covered in a bit more detail in a separate video about rate equations. Check the links in the description below. If a reaction is 0 order with respect to a particular reactant, this means changing the concentration of the reactant has no effect on the rate of the reaction. If a reaction is first order with respect to a particular reactant, this means changing the concentration of the reactant changes the rate of the reaction by the same factor that the concentration was changed. For example, doubling the concentration of the reactant would double the rate of the reaction. Halving the concentration of the reactant would halve the rate. If a reaction is second order with respect to a particular reactant, this means changing the concentration of the reactant changes the rate of the reaction by the same factor squared. For example, doubling the concentration of the reactant would quadruple the rate of the reaction, as the concentration has changed by a factor of 2, meaning the rate will change by the same factor squared, and 2 squared equals 4. Equally, tripling the concentration would make the rate 9 times faster, as this time the concentration has changed by a factor of 3, times 3, and the rate will therefore change by the same factor squared. 3 squared equals 9, meaning the rate becomes 9 times faster when the concentration of the reactant is tripled. Despite the fact this all looks very mathematical and neat, we can only ever find out the order of a reaction with respect to a particular reactant using experimental data. To do this, we have to look at how the rate of a reaction changes as the concentration of a reactant changes. If reaction rate on a y-axis is plotted against a concentration of reactant on an x-axis, then the shape of the graph obtained can be used to quickly identify whether a reaction is zero, first or second order with respect to that reactant. When the reaction is zero order with respect to the reactant, the graph shows a straight horizontal line. The rate of the reaction is always the same, regardless of the concentration of the reactant. When the reaction is first order with respect to the reactant, the graph shows a straight line with a positive gradient. The graph will pass through the origin, and the constant gradient shows that the rate is directly proportional to the concentration of the reactant. As in, whatever factor the x-axis value, concentration, changes by, the y-axis value, rate of reaction, changes by the same factor. When the reaction is second order with respect to the reactant, the graph shows a curved line upwards. Like if the reaction is first order with respect to the reactant, the line must pass through the origin. However, this time the rate increases exponentially with the concentration, given a curved line that starts to go up rapidly as concentration increases. We can also identify whether a reaction is zero, first or second order with respect to a particular reactant by plotting concentration of the reactant on the y-axis against time on the x-axis. The idea here is to look at how the concentration of a reactant changes throughout a reaction. The concentration of a reactant will decrease as a reaction happens, and as the rate of a reaction can change based on the concentration of reactants present, as the concentration of a reactant continues to decrease, then the rate of the reaction may also decrease as well. As the rate of the reaction slows down, the rate at which the reactant concentration continues to decrease will also change. It sounds a lot more confusing than it is. For example, if a reaction is zero order with respect to a particular reagent, then as the concentration of that reactant decreases, the rate remains unaffected, meaning concentration of that reactant continues to decrease at the same rate, given a straight line graph with a constant gradient. If, however, a reaction is first order with respect to a particular reactant, now as the concentration of that reactant decreases, the rate of reaction will also decrease, meaning this reactant gets used up more slowly. This gives a curved graph, with the length of time it takes for the concentration of the reactant to halve, its half-life, being constant. For reactions that are second order with respect to a particular reactant, as the concentration of that reactant decreases, the rate of the reaction will decrease rapidly, given a curved graph. Now, for a first order graph, when the concentration of the reactant halves, the reaction rate halves as well, meaning the reactant concentration will decrease twice as slowly. For the second order graph, however, when the concentration of the reactant halves, the reaction rate quarters. This means the concentration of the reactant will decrease 4 times slower than before. Orders of reaction with respect to a particular reactant can look a bit confusing to start with. However, they can be really useful when studying kinetics and rates of reaction in detail. The overall order of a reaction can be determined by adding up all the individual orders with respect to each reactant. For example, if A plus B react together to form C plus D, if the reaction is zero order with respect to A and first order with respect to B, then the reaction is first order overall, as 0 add 1 is 1. If the reaction was first order with respect to A and second order with respect to B, however, now the reaction would be third order overall, as 1 add 2 is 3. Always remember that orders of reaction and orders of reaction with respect to a particular reactant can only be determined using experimental data. So, to summarize, the rate of a reaction can be affected by the concentrations of reactants reacting. Orders of reaction, with respect to a particular reactant, show the mathematical effect of changing concentration on the rate of reaction. They are written as a small number as a superscript to the reactant in square brackets. Orders of reaction can only be determined using experimental data. If a reaction is zero order with respect to a particular reactant, changing the concentration of the reactant has no impact on the rate of the reaction. If a reaction is first order with respect to a particular reactant, changing the concentration of the reactant will change the rate of the reaction by the same factor. For example, doubling the concentration would double the rate. Halving the concentration would halve the rate. If a reaction is second order with respect to a particular reactant, changing the concentration of the reactant will change the rate of the reaction by the same factor squared. For example, doubling the concentration will quadruple the rate, or halving the concentration would quarter the rate. Reactions that are zero, first and second order with respect to a particular reactant give different shaped graphs for rate of reaction against reactant concentration. For zero order, the concentration has no impact on the rate of the reaction, and the graph is a flat horizontal line. For first order, the rate of the reaction is directly proportional to the concentration of the reactant, and the graph is an upwards straight line with a constant gradient. The line has to pass through the origin, as at a concentration of 0, the rate must also be 0. For second order, the graph has a curved upwards shape, and the rate of reaction changes very quickly with concentration. Reactions that are zero, first and second order with respect to a particular reactant also give different shaped graphs for reactant concentration plotted against time. As time increases and a reaction proceeds, concentrations of all reactants decrease. For zero order, the concentration decreases at a constant rate, as the rate of reaction doesn't slow down as the concentration of the reactant decreases. For first order, the concentration decreases at a slower rate as the reaction continues, as the rate starts to slow down as the concentration of the reactant decreases. The half-life is constant, and it takes the same length of time for the concentration to halve throughout the reaction. For second order, the concentration decreases at a very fast rate and then slows, giving a steeper curve than for first order. The individual orders of all reactants in a reaction can be added together to give an overall order of the reaction. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.